inviting me today to give this lecture, and also my colleagues in Hong Kong that collaborated over the years. Why do I use the title on the snowboard to from China? Actually, a reporter called my daughter earlier today because my daughter was in the communication business, and she asked her, am I going to talk about politics? Well, I don't think I am, because I really don't know enough about politics in Hong Kong. But what I like to do, though, is to take this opportunity to thank people who has helped me along the way, and which include some of the people in the audience here, because we were given this art to talk about the work for which you are receiving this prize, and Professor C.N. Yang wrote to us and he told us about this prize. Now, so what I'm going to go do is so far selected work on DNA tests, and I would like to express gratitude to people who helped me along the way, and then I will discuss some on the current status of DNA tests, and finally, the future prospect in diagnosis in molecular and gene and cell therapy. The disease I will use as a model, sickle cell anemia and thalassemia, both the alpha and beta form. And as Professor Chen pointed out, this is a very common condition worldwide, thalassemia in Southeast Asia and sickle cell, of course, in Africa, but they are found throughout the world. First, okay, the education that led to me to my work. And I remember very well, the high school that I went to in Hong Kong, the Yuet-Wai College. It was at that time situated at #1 Robinson Road. And when I saw this picture, I actually remember the room I was sitting in, and it was right here that I lived. Now, not only I remember the school and the room. Of course, this school is now not there anymore, and with many high-rise apartments in this place. But what really struck in my memory was a very good science teacher that really made an impression on me, and that is Father Lawler, who is a really superb science teacher, and I think that made a mark on me over the years. Then I came into the University of Hong Kong, and then I have also very good professors. Oh, this is, of course, a Lockyer building in Hong Kong. You can see at that time it was beautiful. You can see the sea, the tree, but now it's now sandwiched between many high-rise. I remember, for example, this is Department of Anatomy and Physiology, and I think this is before my time because we didn't have old cars like that. And then when I go to my clinical years, I work in a primary hospital. Again, this is an old picture of primary hospital without all those high-rise. But one thing I want to point out that this is our resident, and they purposely put the nursing quarters far away. And I have very good teachers, Professor A.J. Alex McPherson and Stephen Chang. And these were later joined by Professor Rosie Young, that all of you are familiar with. And then Professor David Todd, came back from England a year or so later. So with these four teachers, I was able to really learn a lot about clinical medicine. And this is my graduation from medical school. And then I spent 2 years at the Queen Mary Hospital doing clinical work. And you can see how hard we work. This, I think, is a Christmas picture with Professor Todd here and myself here and some other friends of ours. And now, after during the pre-med years, I actually managed to publish a paper on hematology, that is the polycythemia hepatocellular carcinoma. And at that time, it was interesting because you notice that the authors are arranged alphabetically. We don't do that anymore. Okay, after that, I decided, unlike most people who graduate medical school in Hong Kong, who have gone to England to get the membership exam, I decided to go to America instead, with a plan to go there for a couple of years before going to England. But before I left, Professor McPherson told me at that time, this was in 1960, he said that, young man, if you want to do research, you've got to learn biochemistry. And which is true. In 1960, most people would go get a basis in pathology, but he had the foresight to tell me that biochemistry is the most important thing of the future. And though I wandered around in the U.S. for a while, and I just want to give you a couple of highlights. I worked in the lab of Vernon Ingram, who discovered that the amino acid substitution in the sickle cell anemia, and he immediately put me on a project on looking at frog hemoglobin and using the bullfrog. And then this is the electrophoresis of the frog hemoglobin, the tadpole hemoglobin in MIT. The reason why he wanted to do that is because he wanted to see, the development change in the frog hemoglobin. That's why using this model. Unfortunately, this model really hadn't worked well over the years because there are very few people working on it. There's one or two groups working on it and hasn't got very far. But that did make an impression on me that it is an interesting problem to study the development of hemoglobin. Then I spent a couple of years at the Royal Victoria Hospital doing more clinical hematology fellowship. And I saw this fetus who has, the homozygous alpha thalassemia associated with hydroxyl fetalis. This was in the 60s. And this is due to severe alpha thalassemia. And then we studied the hemoglobin. They don't make any alpha globin change. And I thought it was an interesting subject, so that's why I decided to use this particular model to further my study in the future. And now then I went to the Children's Hospital in Boston where I began to study these problems. And I used the technique of David Garrow and John Clegg, to study protein synthesis in the thalassemia syndrome. And then what we found furthermore, if we look at the synthesis of hemoglobin of the different alphas in the thalassemia syndrome, the normal is at this level, and as you get more and more alpha globin defect, you get less and less alpha globin synthesis. And I also remember the development of the tadpole to frog hemoglobin, so I decided to study development of hemoglobin in people. And we studied the beta, which is the adult globin, gamma, which is the fetal hemoglobin level, in the newborn, and then months up of age. And you can see here, in normal subject, you have a nice rise of beta hemoglobin, the adult hemoglobin, and a nice fall of fetal hemoglobin. And the patient who have thalassemia will have only a weak rise in this is the heterozygous of beta globin and also a drop in alpha globin. Now, I would like to point out that this normal is who this normal is. And this normal happens to be the baby who was born, my baby who was born at that time, In fact, it was interesting because I was sitting to wait for my wife out there to deliver, and the doctor said she had to go into the delivery room. I gave him a bottle. I said, please give me some cord blood. And then we followed this baby for 5 months, and then she grew up okay. And then, in fact, she even had a baby of her own, but I did not get any blood from her. Then, and of course, the subject is Deborah Khan, who is, I believe, in the audience today. My daughter, Deborah Khan. And now, so we extended this study to show that in the cord blood of beta thalassemia, we can actually detect a lower level of beta globin expression than the control. And also we, of course, at that time, before the DNA technology, we used this method to study the fetal blood. And we look for patients with thalassemia, for example, will not make any beta chain, and heterozygous make a small amount, and then this is a normal, and then the sickle cell patient would make a different globin chain. So, and at that point, I moved to the University of California in San Francisco, at UCSF here. Now, I was very fortunate, as in the case of Kurt Boyer, to meet some people that really helped me along. We went into Mike Bishop and Harold Varma's lab and to learn the new reverse transcription and DNA technology, so that we have new tools for studying the hemoglobin disorder. And we use so-called the solution hybridization method to study the globin gene. Now, nobody ever used that anymore, but this is what is known as hot curve. So, for example, if you study patients who have a severe carrier state of severe alpha thalassemia, you can see that the hybridization curve, this is the normal one. As the disease, when they lose more and more alpha globin gene, the hybridization becomes slower and slower. Although the patient with hydro had no alpha globin gene, there was embryonic globin gene, alpha globin gene. They didn't know at that time. They're still hybridized, but you can see the slow hybridization, whereas the beta globin hybridization is normal. Now, of course, at that time, Andre Doty, who is a very good assistant of mine, we were doing this experiment, and we came across a couple who had previously a child who has homozygous alpha thalassemia. So we used this particular technique to decide if this pregnancy was affected. So this is the hybridization, just single point hybridization, showing this is affected DNA from affected fetuses. These are heterozygous, hemoglobin H heterozygous and normal. And what we determine is the blue triangle here, that this woman's fetus is actually just heterozygous for alpha thalassemia, and that's the normal control. So this was done in about 1975, when we actually did a DNA test on patients for the sake of diagnosis. Now, of course, this is a really difficult technique. In fact, Andre is so good that she can do it. You can see the points are really very well grouped together. In fact, I asked one of my postdoc at that time to do this experiment. He was so frustrated that he decided to leave research. So newer technology came along. And here, of course, I was fortunate to meet Paul Boyer. And as she pointed out, he discovered this enzyme, EcoR1. This is not staged, by the way. He didn't know I was going to talk about it. But it's EcoR1 enzyme. So we use those and using a restriction map to make a diagnosis, which is much easier. For example, I just want to look at this track here. These are the alpha globin gene band, and this is, of course, is sample of DNA that has actually no alpha-globin gene. So it's much easier. And of course, as you pointed out, we know what happened to her boiler. And then Andre also did some, we were still studying alpha thalassemia. So we studied a whole bunch of alpha thalassemia samples. And then one day she said, gee, this is really funny result because this is the alpha globin gene. There are two alpha globin genes using this enzyme called HPA1, 2 alpha globin band. But look at this sample. They have alpha thalassemia because they lose this band. But what is this band over here? Well, this is the normal beta globin band. So to make a long story short, after doing some work, we discovered that this actually band is due to a sickle mutation of the beta globin gene. And we know that the mutation itself does not lengthen the band. And again, to summarize, to make a long story short, what happened is that this is the restriction site for HAPA1. We cut right here. So if you take a normal gene, you have using this as a probe, you have this fragment. Because of the T to C mutation, the enzyme doesn't cut anymore, and therefore you lose this restriction site here, you get a longer band. And that is really how we discover DNA polymorphism. And of course, you know now that this is now using the DNA polymorphism, you can do it to map the population. And of course, it's gone by different names, RFLP or restriction fragment linked polymorphism, because it also includes, for example, di or trinucleotide repeat, giving you different band. And of course, nowadays the term is single nucleotide polymorphism or SNP. And as you know, these are some of the use of DNA polymorphism, and I wouldn't go, I just mentioned genetic diagnosis, linkage analysis, gene discovery, forensic analysis, pharmacogenetics, and now, of course, the haplotype determination, the international effort, including Hong Kong view and Chinese view, to determine HAP. Now, the current approach for prenatal DNA tests is the use polygon-nucleotide hybridization and also microarrays, as shown by Vivian Chen group here in Hong Kong view. And this is one of the polygon-nucleotide hybridization methods showing that you could, for example, dot a number of oligonucleotide with different sequence, and then with the mutated sequence down below, and then if you have a mutation, you will homozygous for this mutation, you will have the hybridizing here and not the normal sequence, and this is a double heterozygous for two different mutations. So this is one of the methods that's being used. And the other one, as I showed, that Dr. Vivian Chen group and Cayman Chen showed that you can use a modified microarray method, and I will not go into detail of this. And the effect of this is using prenatal diagnosis having dramatic in several Mediterranean countries. For example, in Sardinia, the number of newborn with homozygous beta thalassemia born is markedly decreased over the years. And there was some harm there, and one of the reasons is that, of course, there is now treatment by bone marrow transplantation. So some of the parents, they may prefer bone marrow transplantation if they have a compatible donor. So this is not only Sardinia, in Greece, Cyprus, and some European countries, and also in, I'm sure, here in Hong Kong also. So what are the ongoing work is research in prenatal care? The first one would be collecting of fetal DNA or cells from the maternal blood. The reason why do we do that? Because currently fetal cells are obtained by amniocentesis or chorionic villus biopsy. It is now generally agreed by obstetrician that there is a 1% risk to the fetus with these procedures. and hence obtaining fetal cells from the maternal blood will pose no risk at all to the fetus. So that's where research work in this particular area are headed. Now, fetal DNA test using maternal blood. Now, of course, we have to mention Dennis Lowe's work at the Chinese University of Hong Kong on using fetal DNA in maternal plasma. Fetal cells in maternal blood. In Hong Kong, this is Lau has some work on using this for homozygous alpha thalassemia, and our own work on trying to do thalassemia and other genetic diseases. Just very quickly summarize Dennis Lau's work using fetal DNA maternal plasma. You can use it to exclude paternal genotype in prenatal diagnosis. In other words, if the baby has if the father's mutation is different from the mother's mutation, if you don't find a fetal father mutation in the fetal DNA from the plasma, then you exclude the homozygosity. Of course, you will also find a mother DNA. That's why it's an exclusion if the father's mutation is different from mother. You can also use it, especially in Europe now, fetal Rh serotype in Rh negative mothers, because Rh negative is due to deletion of genes. Therefore, if you find that if you don't find any Rh positive gene in the maternal plasma that excludes that the fetus has Rh positive, it's also increased in preeclampsia, and also you can find UV virus in nasopharyngeal carcinoma. As I said, this is the work of Dennis Lowe. And recently, Elizabeth Lau presented some work on fetal cells in maternal plasma in homozygous alpha-thalassemia. And the basis is this. If you use an antibody against anti-alpha, which the fetus will not have if it's homozygous against he is homozygous for alpha thalassemia, and an antibody against zeta, which is an embryonic alpha protein. In the normal, you would, for example, you look at this cell, it will light up with both the alpha and the zeta, and you overlap it with somewhat a yellow color. And if you take a patient with alpha thalassemia, homozygous alpha thalassemia, a cell will not light up with anti-alpha, only the anti-zeta, and therefore, if you see these, it's high likelihood that the fetus is affected by homozygous alpha thalassemia. Now, our own work is you use fetal cells for diagnosis, isolating the DNA from the fetal cells. And the reason for doing that is that now we can determine the genotype of the fetus, whether the fetus of the father or the mother with mutation. So it's not a rule out, but it's a definitive diagnosis. You can use progenitor cells and lymphocytes or trophoblasts on nucleated red blood cells. Now it turned out that progenitor cells and lymphocytes are probably not good because a study by Yankee showed that when she looked at a number of mothers with a number of different previous pregnancies and who had male fetuses and as well as female infants, and look at the years after the last pregnancy, for example, years after 20 years, which she could find lymphoid progenitor that is positive for male DNA. For example, if you look particularly at this one, number 5 here, this mother launched pregnancy for 27 years ago, and yet they was able to detect male DNA. So the progenitor and the lymphocytes are not good. Nucleated cell is good. Red cell is good because the red cell will lose the nucleus, and therefore no more fetal DNA from the previous pregnancy. And I won't bother with the method. Basically, we use a number of separate extraction procedure, and then finally get the cells and do PCR for genotyping. This is showing fetal nuclear red blood cells. You can stain with anti-zeta, which is the embryonic alpha hemoglobin, and then or anti-gamma, which is the fetal hemoglobin, and you can see the nucleus here. It is possible to identify 1 to 2 fetal nuclear red blood cells per mil of maternal blood. However, the method is tedious and inefficient, and therefore we've been trying to use better antibodies, because the antibody we use now to try to enrich a fetal cell is transferrin receptor antibodies, again transferrin receptor, because the red cell makes a lot of hemoglobin, there's a lot of iron, therefore they're rich in transferrin receptor, but of course there's a lot of iron containing enzyme, so every cell also has transferrin receptor, so you can never get really good enrichment. And then we try to have a better way of retrieving nuclear red blood cells. And what we've done now is to use single chain antibody to make single chain antibody that are specific for fetal nuclear red blood cell. And the way we do it is that this is what is shown at the a single chain antibody which contains the variable light and variable heavy region of the immunoglobulin, and then we just clone it out in the phage. I won't go into detail. And then what we do is we use a number of enrichment procedure to enrich this single chain antibody, and just give it. And what happened is we have several that are very good. For example, these are fetal nuclear red blood cells from the fetal liver. And you can see, for example, this particular antibody will interact only with fetal nuclear red blood cells, but not with white blood cell. This one is not as good. This is another antibody because it does react with some. So this is the type of antibodies now that we are using to try to enrich the fetal red cell. And you can see this picture here. This is what we got from the mother's blood, and then we can use, for example, anti-gamma with the fetal hemoglobin, using the phage single chain antibody, and then you can see here, for example, this is the nuclear red cell because you can stain with DAPI for the nuclei, and these are maternal white blood cell, stained also with DAPI. So this is the method we're using, and we are also working with a few companies to see if there are better method of retrieving the cells than just using a pipette to scrape the cells out. So that is where we are now. Now, recently though, we also find out that perhaps we can use trophoblasts, and that we based this study also on Dennis' work, because Dennis showed that the fetal DNA that he found in the maternal plasma actually came from the placenta. And these are trophoblasts. You can see they vary in size from quite large to about 10 micron to about 20 or 30 micron. These are probably hard to find because they will, once they release in the mother circulation, will probably get stuck in the microcirculation. But these are the smaller ones, maybe we may be able to find. And this work is being done at Dongzhou Farm in our laboratory. And we use this method, which is really a filter method to look for this trophoblast. And I just wanted to show this picture showing that using a placental alkaline phosphatase stain, which is specific for placental cell or trophoblast, you can see here there's one cell here, there are two cells here. And these little dots here actually are holes in the filter and not cells. So these will be fetal trophoblast cells that we can recover for DNA test And these two cells, for example, are epithelial cells. They do not stain with placental alkaline phosphatase, and this is presumably not a fetal trophoblast. So this is something that we are working on again. Finally, a few words about treatment of sickle cell anemia and thalassemia. I'll just quickly go through this. It's mostly still transfusion for anemia, iron chelation for iron overload, and prophylactic and treatment of complications such as infection and cardiac and endocrine abnormality,